Hi Science 30s and welcome to How to Solve Pedigrees. We're going to start with a basic pedigree. We're going to run through 4 pedigrees together, and then there's a 5th example that I want you to try on your own. So in our first example here, it's just going back to how do we read pedigrees. So the question asks us in generation 2, what individuals are affected? So if I circle right here, these are my generation 2 individuals. There is the 2, and if we number this properly, this would go 1, 2, 3, 4. So we would say generation 2, person 2, and 3 are our affected individuals. The next part of the question is asking you how many children did they have? Well, in generation 1, 1 and 1, 2, which are these people right here, we just need to follow the line and look at where it's connected. And they had 2 children. So we started very basic, which is great. Fill that in. Pause the video, make sure you have it all down, and let's move on. So now we're going to get a little bit more complicated, and instead what we're going to do is we are going to talk about what types of pedigrees we have. So there are 2 types of learning we've done so far. We have done the learning around the monohybrid, and we've done learning around X-linked. Okay, so I want you to write those underneath on your screen. Now what we need to do is we need to look at this pedigree and decide, is this pedigree showing us a monohybrid inheritance or an X-linked inheritance? That's what this question is asking. Color blindness, what kind of inheritance is that? Now along with this learning, we have also learned terminology called dominant, and we've learned terminology called recessive, meaning big letters and little letters. So when we talk about inheritance as a whole, we are talking about whether or not something is inherited through one trait or on the X chromosome, and is it inherited with big letters or little letters? So let's do this example together. In this example, you're going to notice, and I have 3 individuals who are colored in. They're all male. Now, what you may remember from our learning the other day on X-linked is that when you have an X-linked trait, more males are affected than females. We also specifically talked about color blindness being an X-linked trait. So right now, I'm leaning towards this X-linked being my answer. And the reason for that is because we talked about X-linked showing more males than females affected. So you can write that down, and you can write that that means it is X-linked. Now what we need to decide is it dominant or is it recessive? So what we're going to do is one really easy trick. We're going to look at our very first generation. We're going to see what we have. We have someone who has it. We're going to look at our next generation, and we're going to look across and see that nobody has it. We're going to look at our next one, and then there's somebody who has it. So from generation 1 to generation 3, we skipped a generation. If you skip a generation, that means it is a recessive inheritance. So this particular pedigree is actually called X-linked recessive. So that means if I was to write out the genotype of this individual, I would use X, little c, and then a Y, just like we did in class, because I know that it is inherited on the little letter on the X chromosome. So that's what this particular pedigree is. So again, pause the video, write down what you see here as a way to remind yourself, how do I assess a pedigree? Well, I look for males to female ratio. Does it skip a generation? And then I make a decision. So pause, write it down, and then we'll move on. So now we're going to look at the next one, which is a bit more complicated. So this one now starts pretty simple with, let's look at the number of males and females made by the father and mother in the first generation. So here's our first generation. We're going to count how many females were born to them. So we're going to follow the line over and look that there's 1 here, another line here, that's 1. These just represent twins, so that's another female. Nope, nope. Oh, there's our 3rd female. And there we go. So we have 3 females that were produced by these parents. Now we need to look for males. So I'm going to come along here and notice there's 1 here, 2, 3, and 4 males. So what I have here is I've analyzed the first part of my pedigree, but now I have to do a little bit of investigation because now I have a bit more information on how to solve this pedigree. I'm given the word autosomal. That word is a really fancy way of saying monohybrid, which means we are going to use big B or little b's within our answers. The word dominant means we're going to look at big letters. So we're going to only look at individuals that have this big letter, and that's going to let me know who has the disease. So in this pedigree, we have a monohybrid dominant diagram. So that means any person that's colored in actually has big letters this time. I also know it's dominant because if I look at this, you'll see every single generation has people affected in it. There's people here, there's people here, there's people here, there's people here. It never stops. It always has someone in it, so it's not skipping a generation. So the question is asking us person 3-1. So here's 3, here's 1. What is their phenotype? So remember, phenotype is like taking a photo. It's what I see. So I see a male, because it is 3-1. I see a male, and I see that they are not affected with the disease. Why? Because they're not colored in. And I was told that if it was colored, they would be affected because it's dominant. So my individual 3-1 is a male who is not affected. This contrasts to the next one, which is individual 10-4 over here. This individual is also male, but this time they're affected. It is colored in, and we need to figure out their genotype. So before we figure out their genotype, I'm going to come back here and I'm going to answer the rest of this question. This question says, what is the genotype of this person? So because I said they're male not affected, that means they are going to have little b, little b. The reason for that is because anybody in this diagram that has the disease is going to have a dominant letter. So coming back over here, if you look at this individual is male as well, but they are colored in, so they have to have a big B because we are looking for anybody colored in will have a dominant trait. Now I have to be careful because he's dominant, but I need to figure out what is his other letter. They always come in pairs. So I'm going to trace back and look at his parents. His mom is colored in, so she has a big letter and she passed it on. But the dad is not colored in. He looks a lot like this individual, which we said was little b, little b. So I'm going to add a little b into my diagram to demonstrate that he is a heterozygous individual. So again, stop, pause, put all of these notes down so that you have them. And if you need to rewatch this section to figure it out, that's totally fine. And we're going to move on. All right, one of our very last pedigrees. This one's a little bit more complicated, so I'm going to use my writing tool. Now, we're going to look for individual 2-7. So here's individual 2, here's individual 7. Problem is, I can't tell you the genotype of this individual until I figure out what does this pedigree look like. We now have all the tools to do this. In the first pedigree we analyzed, I said more males than females makes it X-linked. This pedigree is even to the amount of males and females. So we're going to say this is monohybrid or autosomal, like that fancy word we learned last slide. So we have a monohybrid pedigree, and now we have to decide, is it recessive or is it dominant? So again, we're going to apply that little trick we learned. We're going to look at each generation. Somebody has it here, somebody has it here, somebody has it here, but oh, nobody has it here. So it's actually skipped all the way down to the bottom. So we're going to call it recessive. So it skipped, so we have a recessive set of inheritance. So now I can figure out the genotype of this person because I know that I have to use letters, not X's, and anybody colored in has to be recessive. So this person is not colored in, so I'm going to use the big letter B. They're not colored in, so I'm going to say they are big letter B and I don't really know their other genetic, I'm going to go look at their parents to decide what this is. So I'm going to come up here and I'm going to go and say, well, both of these parents have big letters too, because they're not colored in. And then I'm going to go back and look at her siblings. There is somebody here who has the disease. So that means this parent set had to have donated 2 little b's. So each of them has to have a little letter to make sure that this individual has it. Problem is doing this doesn't help me decide what this second letter is, because she could still be big letter B, or big letter B, little letter b. So I'm just going to leave this blank for now. Now, the next question is quite easy because it says homozygous, so same letter, all little. How many individuals have that? Well, we said anybody on this pedigree that is colored in, because it's a monohybrid recessive, will be our recessive individuals. So I'm going to count 1, 2, 3, 4, 5, 6. There's 6 people on this pedigree chart that is homozygous recessive. The next question is a little bit tougher though, because now we're looking for people who have different letters on this chart. We already found 2 of them, and we talked about how we can't know the genetics of this individual, so we probably also don't know the ones of this one. So I'm going to leave these 2, but I'm going to come over here and I'm going to look at these 2. We know he has a big B because his parents gave him one. We know she has a big B because her parents would have given her one. But now we have to look at their children. They have a child that is got the disease, so each of them also get a little letter because they have to make this child that has 2 little letters. So we found 2 more heterozygous individuals. Let's look over here. We have a little b and a big B. Because remember, he's not colored in, so he gets a big letter, but she's colored in, so she gets 2 little letters. Now, if we look at their children, we'll notice that they have children that have the disease. So this dad has to be big B, little b. Meaning, this child here, because the mom has 2 little b's, got a big B from dad, but had to get a little b from the mom. So we've now found 2 more heterozygous individuals. So let's look at this. We, again, cannot tell what is any of these genetics. And the reason for that is because this individual could be big B, or big B, little b. We don't know based off of the parents. So we're going to skip these ones. I'm going to come over here and I'm going to say this individual has a big B. Again, I don't know what else they have because their parents don't really give me a good indication. But this individual has 2 little letter b's because they're affected. What's cool is because of that, we know that all of these children, all of them, have to be big B from mom and little b from dad, because dad only has little b's to give. So all 5 of these kids are also heterozygous. So to answer this question, I would count 5, 6, 7, 8, 9, 10, 11. I found 11 people on this chart who are heterozygous. Now this last question is super hard. I actually can't do this question because if you've looked at my chart, I have filled out everything I possibly can and I've left things blank because I actually don't know. So this question is a trick because it's asking you who on this chart is big letter, big letter. We have 0 idea. There's no way you can figure this out because there's nobody on here that tells us that. So for this one, we're writing 0. So please make sure again you've written all of this down and that you have an idea of what we were doing. Pause the video if you need to or re-watch this section. All right, that leads us to the example I want you to try on your own. So for this example, start by solving the pedigree using the tricks we talked about. Is there more males affected to make it X-linked, or is there an equal amount of males and females to make it monohybrid? Does it miss a generation? Does it skip to make it recessive, or does it show up everywhere to make it dominant? Once you've decided that, try your hand at answering these 3 questions, and we will talk about these 3 questions together the next time I see you. Thanks, and I hope you have a great night.